Now let's learn how k-mean clustering actually works. How we can transform the points that are at left hand side to clusters that are here on the right hand side. How we can do that? So first of all, here we have the initial data, and visibly it looks like there should be 3 clusters of this data. Again, visibly it looks like. How computer will do? Let's see. So as we can see visibly, we can see k is equals to 3. K denotes the number of clusters. Okay, so we'll define k is equals to 3. Well, you might say that, hey, you're cheating over here. So in next videos, we will let you know how you can choose the optimal number of k. For now, let's go with the magical trick, which is the visible trick. So visibly, we can see that here we have 3 number of clusters, so k is going to be 3. So step number 1 is going to be the following. We have to randomly initialize k number of centroids. Again, I repeat, k is 3. So we have 3 random centroids over here, which are denoted by x. First random centroid is neon x, then we have greenish x, and then the third one is the bluish x. How do we define centroids randomly? Since every point is in this 2D system, so every point is denoted by x and y coordinate. So all we have to do is we have to randomly choose 3 x coordinates and 3 y coordinates. That will get us 3 random centroids. Okay, very simple. No hard and fast rule. We randomly have to get 3 centroids. That's it. But if we are in more than 2D space, if we are into 3D space or 4D space, then each centroid is defined by the number of features that we have, right? So step number 1, randomly initializing the centroids. Step number 2, we will take every point one by one. Every point, I repeat, one by one, and we'll calculate its distance with every centroid. For example, here right now, our point of interest is this point. So its distance with neon x is, let's say, A. Its distance with the greenish x is B. Its distance is bluish x is, is C. Okay, what is distance? We have learned the distance measures. You can use Euclidean distance, for example, over here. Okay, now we can see that visibly we can see that, and if you're using Euclidean distance, then you will see in the form of number as well, the distance between the point of interest and neon x, which is denoted by A, is the smallest. So this point of interest will go to the neon color. It will belong to the neon cluster. It will belong to the neon centroid. Okay. Same goes out with every point. Now we are talking about, let's say, this point. Okay. Distance between this point and x is minimal. Bluish x is minimal. Greenish x is a bit more than the bluish one, and the neon x is the farthest one. So this point will belong to the bluish cluster or bluish centroid. Same goes out this point. This point belongs to the greenish centroid over here. So we will repeat this thing for all the points, and by the end of this whole loop, every point will ultimately belongs to some other cluster or some other random centroid. Okay. Now, after one iteration or one loop, the data points would look like this. Okay, these neonish data points are closest to the neonish x. Bluish data points are closest to the bluish x, and same goes out with the greenish as well. Now, this is one iteration, right? Now, the next thing is we have to recalculate the centers of these clusters. For example, visibly we can see the center of this neonish cluster should be this. Okay, so this neon centroid that initially was randomly selected, right? This will travel to here. Well, how we can visibly we can see that, but how we can define it programmatically or mathematically? Very easy. Since we have all of these points, every point is denoted by x and y value. So for example, we have 3 points, 3 comma 3, 1 comma 0, and 9 comma 2. Okay, these are the x values and these are the y values. Can we get their mean? Easily. 9 plus 1, 10 plus 3, 13. 13 divided by 3 is going to be the x of the new position of this neonish x, and 3 plus 2 is 5. 5 divided by 3 is going to be the y-ish position or the y-axis position of this new x, right? So we'll take the mean of all the points in that particular cluster, in that particular color, and we'll take their mean, and that mean will show the updated location of the randomly initialized centroid that we initialized in step 1, right? We'll do it for all 3 centroids over here, or in the bird eye view, if we have 5 centroids, 10 centroids, or 10 clusters, depends upon the number of k. We'll reset all of these centroids based upon the mean of their clusters, mean of their colors. So after this fixation, the centroids will travel to their new locations, and they might look like this. Then what will happen? We'll repeat the step number 2 again, where we will uh, repeat, sorry, step number 4 and 5 again, where we will decide which point is closest to which centroid. This time the points will change their centroids. Why? Because now centroids have changed their location according to the mean in step number 4, right? So we have to repeat step number 4 and 5 again and again, until when? Until when we will reach the final clusters. Well, how do we define, or how do we know we have reached the final clusters, or when do we stop? We have 2 ways. One is when the change in the centroids of cluster becomes 0 ideally, or very close to 0. For example, this bluish point was here in one iteration. In next iteration, maybe it will stay exactly here, and same goes out for this greenish and bluish points as well. Now this will denote that the centroids have reached their ideal location, their ideal position actually. Or if the change is so minimal that we can ignore it, then again we can say we have to stop. Okay. So if the change from the previous iteration to the new iteration in the position of clusters is ideally 0 or close to 0, we can say that we have to stop. Okay. And another way is if we have a huge amount of data and the calculations are taking a lot of time, then we cannot wait for the convergence. This first step is called convergence. Okay, we cannot wait for convergence because it will take a lot of time. Then we will go for predefined number of iterations. For example, we'll define that I'll go for only 50 iterations. In these 50 iterations, if I'll reach convergence or step number 1 condition, that'll be great. If the change in the centroids will become 0 or close to 0, that's great. But if in 50 iteration it doesn't happen, then I'll stop. Okay? So these are the 2 conditions that can help us reaching the stop criteria. Now, the important thing, k should be equals to what? Here we went with our visualization. But it's a 2D data. Visualization is very easy, very quick over here. But what if we are working with 5D data, 10D data, 100D data, where visualization cannot be done? So for example, even if we go with a fluke, we go with a random selection. So on the same data, if we go with the 2 clusters, then the distribution would look like this. The grouping would look like this, which isn't optimal. Visibly, we can see that. But if we go with the 3 clusters, which is the optimal number, then the grouping becomes different, right? If we go with the 4 clusters, then maybe grouping will even change. We go with the 5 clusters, grouping will further change. The question is, the $1 million question is, how do we define k? How do we measure k? How do we get the optimal number of k? Let's learn.